All right, I hope everybody's doing well. So today we're going to be talking about question 2, graph traversals. So let's just hop into it. Okay, so sorry. For the first thing we want to know is that graphs have edges, vertices, and edge weights. And so these would be the edges, these would be the vertices, and these are edge weights. The next thing we want to note is that trees are graphs that are acyclic, and this implies that their absolute value of the amount of, the amount of vertices -1 would be equal to the amount of edges. So in this case, this would not be acyclic because we have this loop here. So this would not be considered a tree. Cool. So the next thing we want to talk about is depth first search and breadth first search. And so the way we would go about doing this is if we were writing it in code, we would use a stack and we would traverse unvisited vertices as far as possible, break ties alphabetically, and like usually this would be specified in the problem. Sometimes in numbers, it's you use lowest number. If there's ever, you can usually clarify this type of information during a test, how to break ties. And then the last part about depth first search and breadth first search is we actually would not utilize edge weights, as we'll see in later problems like Dijkstra's or A-star search. Edge weights will be really important to us. But in case of depth first search and breadth first search, we don't care about edge weights. So the next thing we have is breadth first search over here. And so we want to use a queue. We'd also traverse unvisited vertices based on the number of edges from start vertex. And I'll make this a little bit more clear in the problem, but basically when it says traverse unvisited vertices based on number of edges from start vertex, it goes like this. So we'd go A because, we go to B because B is one away. And then we'd also go to C because C is one away. And then again, we're going to break ties alphabetically, but this can vary problem to problem. It's important to specify. And then we're going to ignore edge weights. So yeah, that may be a little bit confusing at first. And so let's just kind of like hop into a problem. And I guess we can go over depth first search, how this will work. So we'd start at A, and then we'd go, because break ties alphabetically, we go down to B. We continue trying to go. So we go down to D. Again, we'd break ties alphabetically. So we go to E. We say, okay, we're stuck at E. So we go back to our previously visited node, which would be D. We see if we can go anywhere from D. We can go to F. So we go to F. From F, we would go to C because that's, and then we would be done traversing. And let's do a similar one for breadth first search. We start at A. We go to B because B is one away. We look for anything else one away. We see C is one away. So we go to C. D is two away. So we go A, B, D. And then we go back to, we would go back to C. We would go to F. And then lastly, we traverse E because that's the farthest away. So yeah, let's just hop into the problem. Oh, sorry about that. Okay, cool. So just for like a search intro, this is the problem. For the graph below, write the order in which vertices are visited using the specified algorithm starting from A. Break ties by alphabetical order. Notice that we have now introduced edge weights to the graph. So as we learned from the last slide, this part about edge weights, will actually not be used right now, but we'll use it later on when we're doing Dijkstra's. So yeah. Cool. So let's hop into it. So I guess we'll start at A because it says starting from A. And now we'll think. So we break ties alphabetically. This is really important to note. So we have two options of going here. We can either go to G or we can go to C. But because we know we break ties alphabetically, we're going to go follow the path to C. Oops. So the next part is, again, we think about alphabetically. We could either go to H or we could go to D, because we're trying to just keep going down the path as long as we can. So we go to H or D, but then again, D would be alphabetically lower than H, so we go to D. From D, we have another decision. We could either go to B or we could go to F. So these two. But again, we go alphabetically, so then we go down to B. The next way we have to go, we only have E to go down the path, so we go down to E. We see that there's nowhere to go from E, so we want to go back to B. We see if there's any place we can go from B. Clearly, there's nowhere else to go other than the traverse node E. We go back to B's parent, how we got to B, which is D. We then again look if we can go anywhere else, and we see that we have F, and F is our only other node we can go to. So we go to F. Cool. And then this yellow, I guess, is like when we traverse it twice. So yeah. So now from F, we can again follow this path down, and we see that we have G. So we go to G, and then our last node is we'll basically do a bunch of backtracking because like we'll have no place to go. So we'll go back to C, and then we'll lastly go to H. So yeah, hopefully that made sense for DFS.
All right, welcome back. And so today we're going to be talking about BFS. And remember, for BFS, we want the amount of steps from the start node. So just for an example, C would be 1 step away, and then H would be 2 steps away. And again, we're not going to care about these edge weights here for BFS because those don't matter for BFS and DFS. So yeah, let's hop into it. So we're going to start at A, and then we want to look from what nodes we can get to from A. So from here, we can get to C, and we can also get to G. And because we know we want to prioritize alphabetically, when we're adding C and G to the queue, we're actually going to add C, then G, because that's the alphabetical order. So in this case, we're going to traverse C. So yeah, now we want to talk about from C. We can also get to D and H, but these are both going to be 2 steps because, for example, to get to H, we go 1 and then 2. And then to get to D, we go 1 and then 2. So yeah. So we want to think about how we add these to the queue. So we're going to add D and then H to the queue. But in this case, again, they're 2 steps away, and we have this node G that's only 1 steps away. So we're actually going to add G, or sorry, we're going to traverse G next. So yeah, so now we traverse G, and again, we want to add this letter F to the queue because it's going to be 2 steps away again, and we can get there from G. And so yeah, the next thing we have to look at is because we added H and D to the queue before F, we're going to look at H and D. And because F is also like only 2 away, we're going to look at H and D. And we're going to see that D is lower alphabetically, so we're going to add D. And I think this might be a point of common confusion. So basically, the whole idea of like where we traverse next, intuitively, you might go to F because it's lower alphabetically. But actually, we want to think about how we added them to the queue. So because we added D and H to the queue first, we'd actually go to H and then F because of the same distance and because we added H to the queue first. So we traverse it that way. Even though H is higher alphabetically. But yeah. So yeah, there goes H, and then from here we'll go F. And another thing I forgot to mention is because we have this D, sorry, so now we have nowhere to go from this F and this H, so that we know the only place to go here from this D would be B. So go to B, and then the last one we need to traverse is the E. So yeah, I hope that made sense. I think it may be a little confusing on why we went H then F, and I think the important idea to note is just we added D, H to the queue, and then we added F to the queue after we traversed G. And the queue, when we're initially adding to the queue, we only care about this breaking tie alphabetically or by alphabetical order. But like when we're pulling from the queue, we don't reorder the queue based on alphabetical order. So yeah. I hope that makes sense. So yeah, now we're gonna hop into Dijkstra's, and we want to use a priority queue, and the priority is distance to start vertex. Priority start as infinity, and priorities update as nodes are visited with the smallest distance. So yeah, I'll kind of hop into example. Here's like a short little example for you guys. Yeah, cool. So we want to start at A. And we can see here, now we do care about these edge weights. So we can either go to C in 4 steps, or we can go to G in 2 steps. And we know here, we can also see this by the distance to chart table. And we know here that obviously 2 is less than 4, so we're going to go to G. And now we can see here that we can go to F and 2 plus 9, which is 11, an 11 weight, or I guess 11 value. So we can look at our queue, or sorry, not our queue. We can look at our priority queue. And we can see here that we have an 11 and we also have a 4 because we already traversed the G too. So clearly here we're going to want to go to the 4 because that's the shorter distance. Cool. So now from here, we can. So yeah, now we want to look here. We want to update our priority queue accordingly. So we can see here that from A, we can get to D in 4 plus 1, which is 5, 5 weight. And then to get to H, we would do 4 plus 2, which would be 6 weight. So we can update this accordingly, where we have the 6H, and then we have the 5D. And again, we're going to look at from the nodes we haven't traversed, and that we can get to, which is going to be A, H, H, D, F, and we're going to see which one is the smallest. And we can see here that clearly that D is the smallest because it's 5, and 5 is less than 11, and it's also less than 6. So we're going to go to D. Oops. And okay, so I guess the next thing we want to update the priority queue again, and we know it takes 5 steps or 5 weight to get to D, and we're gonna want to do 5 plus 2, which is 7, to get to B, and then we'll update that accordingly. And then the last thing we need to do is we need to know how many steps to get to F, which is going to be 5 plus 8, and that's going to be 13. So, yeah, but I guess the one thing to note about this is that even though we have a weight of 13, because we know we can get there in 11, we actually want to use a smaller weight for F, and so we wouldn't update it with the 13 value, we'd keep it as 11. So yeah, so now we want to look here, out of the nodes you haven't traversed, we can see that H is the smallest. And so yeah, we want to go to H. Cool. So the next thing is we don't have to update our priority queue because H can't go anywhere. And then yeah, so we want to look at our next smallest, which in this case looks to be either B or F. And we can see that 7 is less than 11, so we're going to go B. Okay, so now we want to update our priority queue accordingly. So we can see that takes 7 steps to get to B. Sorry, 7 weight to get to B, and plus 1 to get to E, so that'll be 8. And then from F, we need 11 again. So again, we're going to go to E because that's 8. And then our last node to traverse is 11. So yeah, I hope that made sense to everyone, and I hope you guys enjoyed.